thank you everybody for attending this afternoon. This is the second session of Data Uncertain. Yesterday we had Data Uncertain in the social and health environments, and today we have Data Uncertain in the urban and natural environments. And it's my very great pleasure to be introducing Professor Fang Chen. Fang Chen is a prominent leader in AI and data science with an international reputation. And she's the winner of Oscars of Australian Science 2018 Australian Museum Eureka Prize for Excellence in Data Science. So without any further ado, I'd like to hand it over to Fang. Thank you.
Thank you, Sally, for the introduction. I'm going to talk through some of the examples or projects particularly addressing the theme of this conference, which is uncertainty. So when we're talking about the data science project, actually there's an involvement of two sides. One is, of course, a human being, which we are the center of the decision, prompted by whatever data or whatever machine intelligence. So human beings are complicated creature, we all know. I'm not going to talk this side, which is the chart, the left-hand side, involve, our personality at the level of trust, expertise, our psychological status versus various different behaviors, that how those will have impact towards how we're going to perceive the information and take the information from there. The focus is on the right-hand side, which is machine exhibits various different characteristics, named a few, such as transparency, such as various different probability and performance of the predictions and the risk associated with those. And particularly, I'm going to talk about uncertainty. So as Sally alluded to, I'm going to talk more focus around the urban environment today. And like all the data science projects, we go through the exercise of, define the tasks, understand what sort of data we have and what kind of business outcomes we're expecting. We go through modeling, we look at results, and through validation and communicate or, visualize the result to whoever is interested in seeing them. And right-hand side of the list, the process sometimes we've gone through, and most of my projects go through the same process, which is to understand, domain data, have discussions with the domain expertise to then go through the data, the different cleaning, look at the big picture of the data, started to go through some of the exercise of modeling features, and then go through, present it and go through the cycle with the feedback of the domain expertise, several rounds, eventually have the decision. So each of the steps listed here, from task definition to understand data to modeling validation, all involve some sets of uncertainties. Just the list of some points is not an exclusive list here. For example, when we're talking about tasks, so the uncertainties between the designer task and subtask and needed output, uncertainty between design task and the output through whatever data is existing. Around the data, a lot of issues we don't, I would just name a few, like a quality, integrity, the different volumes and the different, the data, how to get a real-time update, how those ones will have impacted towards the result. Modeling part, a lot around the design and inference, some parameter settings. Also, there's a matching between the data and the model. There's a forever interesting debate of what kind of a model is the most suitable for the data and also to get the outcome. So move to the next, which is the uncertainty, drill down a little bit into the uncertainty task and the data. So normally we go through the brainstorm session and collect the data according to the task and then find the most suitable ones. And somewhat the success come from the feasible goals plus the data. And I'm going to quickly run through some of the definition and give you example of what we did through the COVID as example. So when we define the task and the data uncertainty, it refers to the possibility that we can successfully provide useful task outcome with. And as I alluded to before, there's giving a task pool and the data pool, and then we give the a simple definition of what the certain uncertainty comes from a probability of selecting suitable data sets. And the high probability of selecting the suitable data sets, of course, will result in lower uncertainty. When COVID outbreak happens, a lot of many potential data analysis tasks can be done, include, to looking into the confirmed cases, estimate the impact of different levels of restrictions, social distancing, and social and economic hardship. There's so many different indicators, including mental health and then the impact towards vulnerable groups, etc. So there are many tasks that we can do, and many data are available. However, what is the choice we could make with the task and data uncertainty or certainty balanced? This is the simple map of few tasks. I mean, we've done a lot more, but it is just chosen some of the examples. For example, the task, if you look at the usefulness of for decision making, probably every single column falls into the usefulness, which is a business outcome. One piece of analysis we looked into is the business adversely impacted. Say, for example, which business sector has been impacted severely. Those ones are very useful. However, the indicators or the data has been lagging. We do have ABS, some surveys with some useful information, however, is limited. And then so we put into this category. And homeless risk, another example, is certainly very, very useful. However, the data in terms of where the homeless spread is the data is not very easy to capture, and then a lot of them not updated as well. So this one is looking into the dashboard of the COVID-19 observations, or it's very useful and then can be easily achieved. However, those ones can be found in many various different platforms. Probably the add value won't be a lot. So we picked this area, which is looking into the tenant and the landlord hardship, which the data can be captured through various different data platforms, including the CoreLogic. And then that's very useful to provide the insight into how the whole economic the outlook look like in that aspects. And this is some result looking into this task. This chart shows the volume of the rental space cross from 2016 up to last one we did is up to end of May result. You can see some of the plots there. And this is the median rents over the last, the same period over that one. And this chart is indicated which areas has big changes, a significant job. This is green area, significant job. This is a simple piece of analytics. Simple, I mean, in terms of the complexity is not huge, but is based on the availability of the data and also the usefulness or the potential outcome, certainty of getting outcome to be, then we selected this kind of task. This only the starting point as the teasing part, which is seems obvious part of picking the available data plus the certainty to reach the outcome to start some of the projects. Next example I'm going to talk around is around modeling. Modeling part, how to use some of the structure to reduce uncertainty. The example I'm giving here is around the estimated probability of the water pipe failure. So water pipe is a critical piece of infrastructure in our day-to-day life. When we, every morning you open your water tap, you hope the water is coming through. That's based on the assumption is the water pipe still working. So in Australia, there's a lot of water pipe failures. From top of my memory, even the critical ones, which is the large size bigger than 375 millimeter, which is quite large size. We have probably tens thousand incident or breaks every year. So not talking about the smaller ones, which is the ones that goes to each of the household. And typical methods or traditional industry standard methods is using parametric kind of modeling, which you can see. This is actually a real data plot of wine utilities here. The bottom one is the age of the pipes, and then this one is the failure, number of failures per 100 kilometers per year. And you can see, for example, this category, which is 85 years old pipe, clearly it's not fitting very well with this is the kind of structured parametric learning methods. I didn't mention this line is the sort of like a prediction line based on the parametric methods. And then this is 85 years old pipe. It doesn't fit well. So for that reason, we use the non-parametric and try to avoid the strong assumptions on model structure, so the uncertainty on estimation is removed or reduced, and also model capability growing with the data observations. So you have more data and the flexible structure. If you look at the non-parametric, it fits with the actual distribution better. The bottom one is another example, which is particularly dealing with the smaller size of a pipe. Smaller size of pipe, the big one, which is called the chunkman. Big one, it's rarely to have the failures, but when it's failed, and most of the cases you can get a replacement. And for the smaller ones, most of the cases they happen many failures, just like an earthquake. You have many times struck, but the repairment or renewal solution is to patch them, to allow them to have longest service life. So in order to deal with this kind of a business problem, we actually chosen non-homogeneous stochastic point process based static model to capture the modeling the series of the event, which is the series of the failures on the same pipe, and then the background, the intensity, which is the risk level, is determined by the various different data categories, like their own characteristics of pipes and trigger intensity, etc. So this is one example. The blue curve is demonstrated the Bayesian non-parametric methods versus some standard alone industry methods. Was a difference. And then those ones combine, this part is on the risk map itself, on the probability we also combined the dollar figure, which is called a consequence when you have a break, and then how much dollar is going to cost you to repair it, and combine them together to make a recommendation to provide a prioritized list for renewal. And these end up as the around 17 million US dollars savings by reducing 34% cost. This is a prediction, this is an estimation done by Deloitte's Access Economics around using the one piece of technology I just described as a Bayesian non-parametric on the big chunk man, and estimate to save Australia about $300 million roughly. That's estimated 2015. At that time, the performance of a prediction is around 57 or 60%-ish for forecasting next 12 months top risky pipes. And now it's actually more than, so with all the last five more years data, the performance increased to more than 80%. We haven't done the economic assessment, but the more data is definitely helped to reduce the uncertainty in prediction as well. Last example, I'm going to talk about the data distribution and the impact towards the uncertainty. There's a lot of things can affect. So we all assume that the data, we wanted to have as much as observations as we could. But in reality, probably on the continuous database is almost impossible. But let's just pick something like a sparse data as an example, which we all encounter in many cases, which is we try to predict something, but we don't have a lot of ground truth or incidents to either as a data input to the model or as a validation point to the model. So the example I'm picking is in the sewer, in the water network, in the sewer network. Sewer network, corrosion is heavily impacted by the H2S concentration level, which is a hydrogen sulfide. We use the Gaussian process in this case, which is trying to use very limited data to predict the corrosion level. So you can look in, this is demonstration, which is when the observation are sparse, and then the envelope, which shows high uncertainty, prediction uncertainty is higher. And when you have more data points there, low certainty is presented. In reality, you can see this, this is the prediction. Look at the right-hand side is H2S estimation over the real time, over the whole network. Different color shows the risk level. The darker the color, reddish color is more risky. And look at here, which is you see some of the lines are thinner, some lines are thicker. So the thicker lines representing higher uncertainty when we estimate using the model to estimate the risk. So those gives the operators a bit of a sense of feeling. One is what kind of estimated risk level, and then second is with that risk level estimation, how much uncertainty actually involved in, so that people can make a decision in a more informed way. So this is conclude my presentation. We've done a lot of work with various different projects, governments, utilities, transport, telecommunications, mining, education, retail, finance, name them, and have quite some prizes. But all those attributed to understanding data, understanding the potential outcome which can be derived from data, and constructed the model to provide the best performance. Meanwhile, go through the rigorous testing process, which is validation against the ground truth, so that make sure those results can be really used in daily life or in operations. Thank you. I think I'm running out of my time. All good.
Thank you, Fang. That was very interesting and also